Hello everybody. In today's video we're going to be going over potential difference in the Millikan oil drop experiment. So to begin with, we're going to be discussing potential difference. Now, potential difference as a concept is very important for not only electrostatics, but will be key in the next section, which is circuits and current electricity. So to begin with, I'm going to do a comparison between electric potential and gravitational potential. Now, in gravitational potential, there's a very familiar formula that we have, and that is the potential energy for gravity is equal to mass times g, which is the gravitational field strength, which on Earth is 9.81, times the height. Now, electricity has a very similar formula to that. Potential energy of a charged particle is equal to the charge times the electric field times the distance. And hopefully right away you can see some parallels between the two formulas. Charge is pretty equivalent for mass in terms of electricity and gravity. They're very similar to each other. We saw that back in the Coulomb's law electrostatic force formula was very similar to the gravitational force formula. Electric field and gravitational field, E and G, are also very similar to each other. Now, the main difference that we're going to see with this unit is we're very used to G not changing at all, the gravitational field strength remaining constant. That's because on the surface of the Earth, it does stay relatively constant, while E, over in the electric potential side, E does change quite often. Basically, the only time it doesn't is inside parallel plates, which of course is what we're going to be doing most of our calculations in, but we're still going to deal with times where it changes. And then of course, height and distance are very equivalent to each other. Now, because the electric field and distance often change with each other, if we're talking about something other than a parallel plate, so we're talking about a singular charged particle, as you move away from that singular charged particle, not only is your distance increasing, but also the electric field is weakening as you get further and further away. It has less of a pull on it. So because both of those often change together, when in electricity, we often combine those two terms. And that is what we call potential difference, which is given by the symbol V. And we often name it after its unit, which is voltage. So you'll often see the term voltage being used, but potential difference is the technical term. If you're looking at any type of test question or anything like that, they're going to use the phrase potential difference because that's what it is technically. Even if we use the unit often for the name, it's still officially named potential difference. So the potential difference really is the combination of the electric field and the distance part. Now you can see at the bottom of this section, we have this formula. This formula is work, W, which we've seen before, is equal to charge times V. It's basically this. So it's the amount of work it takes to move up a charge is the potential difference. So the charge times the voltage will tell you the amount of work it takes to move a charge. And the equivalent side for gravity, something that should be very familiar, is the work to move up a physical object, to physically pick something up, is mass times the gravitational field strength, which is 9.81 on Earth, times the height. Now, we can keep these very separate because G tends to be the same in all cases. For Earth, we tend not to look at this formula outside of Earth, at least very often at all. So you can see at the bottom here, we have two pictures. We have the object or the charge being picked up through the electric field, and that takes a certain amount of energy to physically lift that up. And how we would calculate that energy is we would do Q times this value, voltage. At the same time, we have the physical object being picked up from the ground, being lifted up into the air, and you can see that takes a certain amount of energy to lift that up. We're very familiar with this idea, and that's given by the formula mgh. So these formulas are very similar to each other. What I want to point out is what voltage is it's equivalent, it's equivalent to the G times H over here, because that's what's going to be changing in a formula. Now, in terms of calculations, voltage questions tend to be very straightforward for when we're talking about something not in a circuit or current electricity. So here we have a math example using this idea of potential difference or voltage. So in this case, we have a moving point charge. So a charge is moving through an electric field. The charge has 3.2 times 10 to the minus 19 coulombs, so maybe something like an alpha particle. And it's moving through an electric field, and it requires 4.8 times 10 to the minus 18 joules of energy. So to pick up or to move this particle in this field, it takes a certain amount of energy to do that. Now we're going to calculate the potential difference between these 2 points. So the potential difference is given by this formula right here, which is the potential difference is equal to the work divided by the charge. So we're going to be calculating the V over here. So all I have to do is plug in my values for work, which is the energy over here, so the joules, and then the charge at the bottom. And when I do the math out, I get 15 volts of potential difference. Now, right here, sometimes people get a little confused. Now, pretty much in every case in physics so far, the variable and the unit have had different symbols. This is to, lower the amount of confusion. In a lot of cases, it's very inconvenient to have the same. But in this case here, just know that V is both the symbol for potential difference, and it is also the symbol for the unit volts, which is the unit for potential difference. So that's why we're getting V is equal to 15V, because this V is our variable, potential difference, and this V is our unit for volts, or voltage. Okay, now we're going to be looking at the electron volt. So the electron volt is a certain unit, so it's not an SI unit. It's instead a unit for energy. So the electron volt is a unit for energy, not a unit for potential difference. And it is the energy required to move one elementary charge through 1 volt. So this is another unit like elementary charge that's very useful for when you're dealing with things that are very small. So this will allow us to make these calculations with more normal size number. So rather than like in the last example, we had to deal with a lot of, times 10 to the negative whatever. We had to deal with these very small numbers. But this unit is one that's a very small unit, so we're allowed to do calculations with very normal size numbers if the situation calls for it. So this is the formula that we saw before, just rewritten. So if we have 1 volt times 1 elementary charge, that is equal to 1 electron volt. So again, keep in mind, it is a unit for energy. A lot of people think it's a unit for voltage. It's not. It's a unit for energy. Now this is the equivalent of 1 volt times 1.6 times 10 to the minus 19 coulombs, which is equal to 1.6 times 10 to the minus 19 joules. So in other words, because these are the same, our conversion rate is 1 electron volt is equal to 1.6 times 10 to the minus 16 joules. This number, of course, is one that we're very familiar with, so we should be pretty comfortable with doing conversions. If you need to convert between coulombs and elementary charges, you know how to do that with the same number. It's the exact same way for converting between electron volts and joules. So when to use electron volts? Basically, if the question is given to you in elementary charges, or it asks you to find something in terms of electron volts, then you can feel free to use these simple units. Otherwise, if you're given a lot of SI units, if it's looking like everything is in joules or in coulombs, stick with the SI units. But if it's in elementary volts, electron volts or elementary charges, feel free to use these units. All right. Now we're going to jump to a little bit of a different topic, which is the Milken oil drop experiment. Now this could have fit earlier on in the unit talking about Coulomb's law, but I like talking about it at the very end to discuss, kind of summarize some of the stuff in the unit. What the Milken oil drop experiment was our how we figured out what the elementary charge was, this 1.6 times 10 to the minus 19 coulombs. So we didn't always know that was, the charge of electron. We had to figure that out. And it actually took multiple scientists to get to this point. It took J.J. Thomson to figure out what's something called the charge to mass ratio, but it wasn't up until Milken who was able to, he devised this experiment and conducted it, and we were able to actually figure out what the charge and the mass of an electron is. So let's take a quick peek. We're going to look at this video a little bit, and I'm going to just talk through it. All right. So in the milk and oil drop experiment, the idea is we have this. Let me just use my mouse a little bit here. We have this oil drop sprayer that sprays this very fine mist of oil in this chamber filled with water. And it separates all of this oil out into these very, very small droplets. Some of these droplets will fall through this hole, which is located in the middle. And as it falls through the hole, we're going to fire X-rays at it. And the purpose for that is when an X-ray hits an atom, it has a chance to excite the water molecules nearby, basically giving the oil a couple extra electrons. So the idea here is we're dropping oil down in these very, very small droplets that do not weigh that much, and we are giving it an electric charge. And then what we're going to do is we're going to charge these two plates that's falling through. So the ones with extra electrons stuck on them are going to start to be attracted to the plate above. So where gravity wants to pull it down, because that's what gravity does, but the charge on all of these oil drops wants to keep it up. Once you turn it up a little bit, you'll see that these drops are slowing down. Some of them are raising up, but they're doing so at different times. The goal of this experiment is to try to figure out how much charge is on every drop. And that's by looking at its mass times its gravity. Mass times the gravitational field strength, and then comparing it to the charge and the electric field that's between these two plates. And if you can make that comparison, then you can figure out how much charge is on the oil drop. Now, if you do this 1,000 times, 10,000 times, what you begin to notice is that these charges all have a common multiple. And that common multiple is that 1.6 times 10 to the minus 19 coulombs. So none of them probably had just one electron on them, but they all had some multiple of electrons, as we talked about quantization before. So to summarize, we have the fine mist over here, and some of the individual very, very small droplets of oil are falling through, and those oil gain charges from an X-ray machine, so it just gives it some electrons. And then we have some charge plates up here, which create the electric field. And what that gives is a gravitational force going downwards from the Earth and an electric force going upwards. And if you fine-tune that electric field, so you get it so the drop stops right in the middle and just hovers there, isn't going up, isn't going down, but instead is at equilibrium, we can calculate how much charge is on that by finding f of e, by knowing f of g. And with that, we can figure out the charge on the oil drop, and then do this enough times, you'll notice that they all have a common denominator, which is that 1.6 times 10 to the minus 19. All right, so let's take a peek over here. So I have my answer down over here, but let's kind of go through it slowly. So if I have an oil drop with a very small mass of 4.8 times 10 to the minus 14 kilograms suspended in an electric field, there's the electric field, 4.2 times 10 to the 15 newtons per coulomb, what is the charge of the oil drop? The first step is to figure out the force of gravity on that oil drop. And we're just going to use the very traditional weight formula over here. I have the mass. We're on Earth, so I know the gravitational field strength is 9.81. So I just need to multiply the two values together. I apologize, this is supposed to be to the minus 14. And so when you multiply the two values together, you get 4.6 times 10 to the minus 13 newtons. So if that is the force of gravity on the oil drop, I know that needs to be the electrostatic force on the oil drop too, because again, it's hovering there, it's at equilibrium, both the forces are even with each other. So I'm going to use the electric field formula. I know this force is the same as gravity because it's hovering there. I'm trying to find the charge on the oil drop, and I have the electric field because it's given by the problem. I just need to plug in these values, and when I get a charge, I get 1.2 times 10 to the minus 18. Now, this by itself does not give us anything interesting about an electron. But again, it's when you get thousands of results and you find out the common denominator is, which this, if you divide it by 1.6 times 10 to the minus 19, you do get a whole number from it. So this, is a possible answer to the Mielken oil drop experiment. No whiteboard questions for today. That's pretty much it. If you have any questions, always feel free to ask. Have a good one.